has a message.
Stay tuned later in this video for a special presentation by Dr. Alexander Spamilton.
But first,
All right, folks, we want to talk about the derivative as an instantaneous rate of change. When you've got a function that's algebraic and you want to get its derivative at a point, you use the limit definition of the derivative, the limit of the difference quotient, to get the instantaneous derivative at a point. When you're looking at a graph, you know that the derivative of f at x, like f prime of x, is the slope of that function at x. So graphically, the derivative is the slope of the function at some independent value or at some point. But in word problems, the way you express a derivative is as an instantaneous rate of change. If a difference quotient represents an average rate of change in word problems, then the limit of the difference quotient, i.e. the derivative, represents the instantaneous rate of change in word problems. That's how you do word problems with derivatives. So let's start with the first familiar context, then we'll get to some more unfamiliar contexts. X of t is the position of a particle on an x-axis. In other words, a particle is moving back and forth along an x-axis, okay? X of t is the position of a particle on an x-axis in feet at time t in seconds. All right, so this is a position function. This position function x, in goes time t in seconds, and out comes position x of t in feet. Right, so if we want to talk about x prime, which is kind of the derivative function, get the original function f, now I got a derivative function x prime. What's going to go into x prime? The same thing that went into x. Time t in seconds. Very formulaic, right? What's going to come out? The instantaneous rate of change. Now I'm calling it IROC. That's not a thing. You can't write that on tests. But for ease sake here, IROC, an instantaneous rate of change of position, that's this, x of t, with respect to time, that's this, in feet per second, in feet per second. So see, really, this is easy. You have your original function, independent variable identified in context, dependent variable identified in context. Units of the independent variable identified in context, units of the dependent variable identified in context. No problem, it's a position function. Getting the derivative. Use same exact independent variable, same exact units for the independent variable. For the dependent variable, it's going to be the instantaneous rate of change of this guy's dependent variable with respect to this guy's independent variable in this guy's dependent variable's units divided by this guy's independent variable's units, feet per second. And this works every time. By the way, what do we call an instantaneous rate of change of position? With respect to time, we call it velocity, which is why this first derivative x prime is actually giving you the velocity of the particle in feet per second at time t, right? Okay. So let's practically interpret this. What does x of 6 equals negative 3 mean? It means at time 6 seconds, the position of my particle is at position negative 3. What might that mean? Well, if here's an x-axis, and we'll say this is position 0, where are we going to be at time 6 seconds? At time 6 seconds, it looks like we're right here. The particle's right here at negative 3 meters. Negative 3 feet. Meaning 3 feet to the right of the origin. Okay, what does x prime of 6 equals 1.5 means? This means the derivative of x at 6 is 1.5. In context, it means the instantaneous rate of change of position with respect to time at time 6 is 1.5 feet per second. In other words, at time 6 seconds, the particle is moving in the positive direction at a rate of 1.5 feet per second. So it's got a velocity of 1.5 feet per second moving towards the right. So at time 3, this particle is moving which direction? Left or right? It's definitely moving at time 6. From position 3, at time 6, this particle is definitely moving to the right because it's got a positive velocity. If this positive velocity, this instantaneous velocity, held up for the next 2 seconds, that means I would cover, what, 3 feet, and I'd be back to the origin, if it held up. All right, now we're going to look at this in other contexts, and you'll see it's very formulaic, helping you with word problems.
This problem looks hard. Who are you going to ask for help?
We could ask Professor Alexander Spamilton. I heard he's wise in the ways of math. What's that, Spamilton? You got some mint to eat and some basil? Okay, well, I can answer the question for them. All right, folks, check out this example, a little less familiar, right? You'll see how formulaic derivatives are in word problems. A manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of fabric is F of X, dollars. And F of X is nicknamed C for cost. Okay, make sure we understand here what a bolt of fabric is. Have you ever been to Joann's Fabric? There's kind of, it's rolled up like you would wrapping paper, and you unroll the bolt, and then you say you want this many yards of it. They cut it off, you take that home. Well, that much fabric had a cost to produce it, and the whole bolt had a cost to produce it. So that's what we're talking about here. So the question is, what is this f function? What goes in, what comes out? That's the question you always ask. What's the independent variable meaning, the dependent variable meaning, and the units? First, on the original function, f. Well, it tells us what's coming out. The cost of producing X yards of fabric is C equals F of X dollars. That's what this function's coming out is, right? The cost F of X of producing the fabric in dollars. Well, what's going in? That bolt has width, but it also has length. The length of the fabric is what you're really measuring. The length X of fabric produced in yards. What goes into the function, length X of fabric produced in yards. What comes out, the cost F of X of producing that fabric in dollars. I got it established. Independent variable, dependent variable, in context, units, units. Now I go on to the derivative function. If this is the original function, this is the derivative function. If we were dealing with position, this would be velocity, right? But we're not. So what goes into the f prime function? Here's the formulaic part of it. Exactly what went into the f function, the length x of fabric produced in yards. And what comes out? Very formulaic. The instantaneous rate of change of the cost, f of x, of producing that fabric, that's this, with respect to length x of the fabric produced, that's this, in dollars per yard, that's this, over this. Do you see it? Again, what goes into the function? What's the independent variable in context and its units? Same as the f function. What's the dependent variable coming out? The instantaneous rate of change of this, which is f of x, with respect to this, which is x. What will the units be? This over this. Works every time. Now sometimes it's not so easy to understand what this is in context. You're trying to use words to describe to a person. So let's try that. What does f of 500 equal 1,000 mean? Well, what function are you dealing with? The f function. All right, f of 500 equals 1,000. Length goes in, cost comes out. Got it. If I am producing 500 yards worth of fabric on a bolt, that's going to cost me a total of $1,000 to produce. Okay. What does f prime of 500 equal 1 mean? Well, when I'm producing a total of 500 yards of fabric, the cost of producing fabric seems to be increasing at a rate of $1 per yard. What does that mean? Let's think about it. What would you expect, at least up to a certain volume of business? And maybe it's going to start down here at 0, 0, but we'll do that for simplicity's sake. As the total length of fabric produced increase, in other words, produce more and more fabric, right? What would you expect the cost to do? Increase linearly, like as the length goes up, the cost goes up linearly? Or would you expect there to be kind of economies of scale, so that as you increase production, measured here in length of fabric, increase production here to a certain volume, then your costs are going to rise, but not quite as fast, you know, as your fabric is being produced. So what might you get? You might get some curve that looks like this, at least up to a certain volume. Something like a root function type thing. Well, what do you notice about the average slope of this root function from, say, 0 to 0 to 500? Well, it looks like the average rate of change here from 0, 0 to 500, 1,000 would be essentially 1,000 over 500, which would be a rate of change of 2, right? There's an average rate of change of 2. What does that mean? For every additional yard of fabric you produce, or for every, over this average period of time, from 0 to 500, right? Not period of time. In producing 500 length worth of fabric over that interval, it's going to cost you on average $2 to produce every yard of fabric. But what do you notice about the slope by the time we get to 500? What has the slope gone to? Well, F prime of 500 is 1. That's my little red slope of 1, which has a rise over run. A rise in total cost, a run in length. Well, it looks like it's getting more shallow, which you would expect. So now what you'd say is right here, once we've produced 500 yards of fabric, well, now the rate of increase of cost is really just $1 per yard, right? So I can produce more length for less overall cost, and you can see that reflected over here. So how would I say it? Well, when I'm producing 500 yards worth of fabric, well then my cost is increasing at only about $1 per yard, which is a lot better than it was before, which is increasing at an average of about $2 a yard. Maybe here it was a $5 a yard, $4 a yard, $3 a yard, $2 a yard, you know, but down over here, $1 a yard. Pretty great. Okay, folks, and this is what I mean. There's a formulaic piece, and then there's also a thinking it through piece. So you think it through, use your formulas in combination to come up with something that makes legitimate sense. Thanks.